Hi guys, up to now we have been focusing on single phase transformers. There we saw efficiency, voltage regulation, equivalent circuit and solved some problems on the single phase transformer. In this lecture what we'll be doing is, we'll be moving towards the three phase transformer and we'll see what are the construction of those transformer and what is the working of those transformer. So first let us understand the two type of transformer based on application, that is power transformer and distribution transformer. Now what is a power transformer is, it is connected to a power station, that is it is connected just after the synchronous generator. Synchronous generator will generate the power, then the power transformer will be used to step up the voltage. Why do we step up the voltage? To reduce the losses. See what happens, if power which is equal to Vi cos phi is considered as constant, then as we increase the voltage, current will reduce. Due to reduction in current, the losses, which is I square R, they will also go down. So we generally transmit the power at higher voltages, and to transmit the power at higher voltages we use the step up transformer. That transformer is connected immediately after the generator is called as power transformer. But the transformers that you might have seen near your homes are used to supply the power to the consumers. They are used to distribute the power to the consumer and are called as distribution transformer. So that is the basic difference between the functionality of these two transformers. One is used to step up the voltage for transmission, other is used to distribute the load to the consumer. Next is, this power transformer has higher power rating greater than 1 MVA and high voltage, whereas distribution transformer has a rating less than 1 MVA and it is low voltage because it transmits the power at 220 or 230 volts. So it is a low voltage transformer. Now since power transformer is connected to the generator, it will always be operating at a constant load, that is full load. So power transformer always operates at full load since it is connected to generator. But this distribution transformer is connected to consumer. Now consumer may switch on the tube light, consumer may switch on the AC, cooler, something like that. So the load will be fluctuating. Sometimes something may be on, other times that may be off. So fluctuating load. Okay. Load is not constant, load is always fluctuating. Load is variable. Okay, because it is connected directly to the consumer. Now for maximum efficiency in single phase transformer, we saw X is equal to under root Pi by PCU full load. Now this power transformer is always operated at full load, so copper loss will be equal to full load. So here maximum efficiency occurs at X is equal to 1, because copper loss is always equal to copper loss at full load. So here full load copper loss becomes critical and we need to take care that full load copper loss is minimum, because the copper loss at any time of the day will be equal to full load copper loss. Why? Because transformer operates at full load. That is why we need to minimize these losses to improve the efficiency of the transformer. But if we talk about distribution transformer, it does not operate at full load. So here X will be less than 1. For maximum efficiency it will be less than 1. Now the thing is, since transformer is on for the entire day, iron loss will occur for entire 24 hours. But copper loss will depend on the load. So here iron loss is critical. To improve the efficiency we need to reduce the iron loss, because copper loss is variable as it depends on the load. So we'll need to take care about the iron loss and we need to make it as low as possible. Okay, here specific weight of transformer is less, here specific weight is more. Okay, so while designing we need to take care in distribution transformer that iron loss should be less, and in power transformer that copper loss should be less. and the specific weight of power transformer is less as compared to distribution transformer. So that is the basic functionality and the basic uses of the power and the distribution transformer. Power transformer, do not confuse by the name that it transforms the power. It just transforms the voltage from a low voltage to a high voltage. It is called as power transformer because it is connected to a power station. It does not transform the power. Power will always be constant whenever we are talking about the power transformer. It cannot be used as an amplifier. So whichever type of transformer you may use, power will be constant. Now let us talk about harmonics in case of three-phase transformer. Up to now we studied about harmonics in a single-phase transformer. There we saw whenever the flux is sinusoidal, magnetizing current will be peaky, and if magnetizing current is sinusoidal, then flux will be flat-topped, which will lead to a peaky EMF. So let us talk about what happens to harmonics in a three-phase transformer. So first I am considering 3n plus 1 harmonic. In this also let us consider 7th harmonic when we take n is equal to 2. Now what will happen to IA? It will be Im sin 7 omega t, IB Im sin 7 omega t minus 7 into 120. 7 into 120 can be written as simply 840. Okay. Now 840 is 720 plus 120. So I can write it as 7 omega t minus 120. Because 720 plus 120, 720 is 360 into 2. So I have removed that 4 pi angle or 720 degree angle because it does not make a difference. IC will be Im sin 7 omega t plus 840 because plus 120 into 7. Again it can be written as sin 7 omega t plus 120 degree. Now if you see, the phase sequence is A, B, C. That is a positive phase sequence. So 7th harmonic is a positive sequence harmonic. Now we do understand whenever we have a balanced three-phase voltages or currents, the sum of those will be 0. Okay. That means if I take IA plus IB plus IC, it will always be 0. For a balanced three-phase connection, the sum of three-phase currents and voltages is always 0. That means these harmonics can flow in star as well as delta connection. See, if we take a star connection, what will happen is, let us say this is IA, this is IB, this is IC. Now applying KCL at this node, I will get IA plus IB plus IC is equal to 0. And this relation we were getting from the harmonic currents also directly, because they were balanced, their sum should always be 0. And this property is satisfied by KCL also here. That means these harmonics can exist in the star connection. Okay. So 7th harmonic is a positive sequence harmonic. It can be present in star as well as delta connection. Next let us consider 3n minus 1 harmonic. In this, if we take n is equal to 2, we will arrive at 5th harmonic. So let us see what will happen. IA will be Im sin 5 omega t. IB will be Im sin 5 omega t minus 600 120 into 5. Now it can be written as Im sin 5 omega t plus 120. What I have done is, I have made this 600 is equal to 720 minus 120. So minus minus will become plus, it will be plus 120. IC will be Im sine 5 omega t plus 600. Now this 600 can be written as 720 minus 120. So it will be minus 120. Now if you see phase sequences A, then C, then B. This is a negative sequence. Though it is a negative sequence, still it is balanced. That means IA plus IB plus IC will always be 0. That means this harmonic can also exist in star as well as delta connection, because the sum of currents is always 0. Okay, but remember 3n plus 1 harmonics are always positive sequence harmonics, and 3n minus 1 harmonics are always negative sequence harmonics. This concept will always be used in other machines also, so do try to keep this concept in mind. Okay, now let us move to 3n harmonics, that is my triplen harmonics. Let us keep n is equal to 1. Let us talk about third harmonic. So if we write IA, it will be Im sine 3 omega t. If we talk about IB, Im sine 3 omega t minus 120 into 3, that is 360. It will again become Im sine 3 omega t. IC will be Im sine 3 omega t plus 120 into 3, that is 360. It will be Im sine 3 omega t. Now if you take IA plus IB plus IC, this is not balanced because they do not have 120-degree phase difference between them. So these are not balanced currents. If we take the sum, it will be 3 Im sine 3 omega t, which is not equal to 0. Okay. So if we take star connection, let us say, if we take star connection, then according to KCL, IA plus IB plus IC should be 0. Which implies 3 Im sine 3 omega t must be 0. It implies Im sine 3 omega t must be 0, which means third harmonic is 0. So third harmonics cannot exist in a star connection. Okay, third harmonics are absent in a star connection. But what if I take a neutral connection? This type of star connection is called as star with isolated neutral, because neutral is disconnected. Suppose I connect the neutral to ground. Now In will be equal to Ia plus IB plus IC. Which is equal to 3 Im sine 3 omega t. Now it does not need to be 0. It is equal to neutral current. So third harmonic Im sine 3 omega t will be equal to neutral current by 3. So in case the neutral is connected to the ground, the third harmonic is non-zero in case of three-phase transformer star connection. What about delta connection? If we take a delta connection, let us say A, B, C, IAB, IBC, ICA. Okay, IAB is equal to IBC is equal to ICA. For third harmonic, all are Im sine omega t. So that means my third harmonic can flow in closed loop like this. So here third harmonic can be present because it can flow in a closed loop. But what about line currents? In line currents, Ia what I will say? IA will be equal to ICA minus IAB. Since both are equal, this will be 0. So third harmonic current will be absent in case of line current, but it can exist in phase. So that means third harmonic currents require one of the two things. Either there must be a path to the ground, or there must be a closed path for the flow of third harmonic currents. In delta connection we have a closed path, so third harmonic currents can flow. And in star connection, if we connect the neutral to the ground, then only the third harmonic currents can flow because they get a path to the ground. So that are the two cases in which third harmonic currents can flow, otherwise third harmonic currents are absent. So this is about the harmonics in case of three phase. So what have we observed? 3n plus 1 and 3n minus 1 harmonics can always be present. But for triple n harmonics to exist, we need either a closed loop or we need a path to the ground. Okay. But there is no such necessary condition for the case of fifth and the seventh harmonic, that is 3n minus 1 and the 3n plus 1 harmonics respectively. Okay. Now let us see what are the various type of constructions in case of three-phase transformer. Now one possible way to construct a three-phase transformer is to connect three single-phase transformer in either a star or a delta configuration. But what happens is the cost is higher. Why the cost is higher? Because the insulation will be more, the copper requirement will be more, and the transformer will be bulky. So what do we do is, we take different constructions for case of three-phase transformer. We do not simply connect the three single-phase transformers in star or delta. Now this is my first construction. It is called as three-limbed core type transformer. Okay. Because if you see here, core is surrounded by the winding. That is the same condition as we saw in single phase core type transformer. Three limbed because we have three limbs here. Okay. Since we have here three limbs, it is called as three limbed core type transformer. So some of the features are, all limbs have equal area. Okay. Here all limbs will be having equal area. Here copper is less. Copper requirement is lesser, similar to the core type transformer. Insulation requirement is also lesser. Okay. And it is high voltage, low kVA transformer. It is used for high voltage and low kVA. Now since it is the core is surrounded by winding, its mechanical support is less. Similar to our core type transformer, here mechanical support is lesser. Now let us talk about third harmonic flux in this. Now this A phase, see, this A phase will be generating a flux like this. B phase will be generating a flux like this. C phase will also be generating a flux like this. Okay. Now, when all the phases are generating a flux like this, there is no closed path for the flow of flux. If we take at this point, A flux will be coming like this, B will be coming like this, C will be like this. So we have to take phi A plus phi B plus phi C to be 0. Just like KCL I am applying for the magnetic circuit. I am applying the rule of KCL to the flux for the magnetic circuit. So sum of all these three fluxes should be 0. That means my third harmonic will be 0. So third harmonic flux cannot exist in a three-limbed core type transformer. That means third harmonic EMF will also not be there. Okay. If flux does not contain a third harmonic, EMF will also not contain any third harmonic, because EMF will be derived from the derivative of flux. Is it fine? In case of three-limbed core type transformer, we do not have any closed path, so third harmonic flux can never flow. Other transformer is the analog of shell type transformer in a single phase. Okay. As we saw shell type transformer in single phase, here we have 5-limbed shell type transformer. Okay, here we have 5 vertical limbs, so it is called as 5-limbed. Okay. So first feature is outer limbs have lesser cross sectional area. As we saw in shell type, outer limbs have half the area of the inner limbs. Okay. Here copper and insulation are more. Okay. Here it is used for low voltage and high kVA. Okay. And it has more mechanical support as compared to core type transformer, because it has additional mechanical support of these two limbs. Okay. Now let us talk about third harmonics. That is the most important thing. So here if we see, if it creates a flux, it can flow like this in a closed path. It creates a flux, it can flow like this in a closed path. So here we have closed paths available for the flow of flux. So third harmonic flux can exist. Okay, that means third harmonic EMF can also exist. So that is the difference between 3-limbed and the 5-limbed type of transformer. In 3-limbed, third harmonic flux can never exist, but in case of 5-limbed, third harmonic flux can exist. Hence, EMF will be non-sinusoidal. Okay. That is the difference between 3-limbed and the 5-limbed type of transformer. Okay. But we studied in case of single phase transformer that whenever the current has third harmonic, flux is sinusoidal. Whenever the flux has third harmonic, current is sinusoidal. Now in delta connection, I told you third harmonic current can exist. Third harmonic current can exist. So it means flux is sinusoidal. Since current has third harmonic, flux will be sinusoidal. In star connection, third harmonic current cannot exist. That means flux will be non-sinusoidal. Okay. Whenever current has third harmonic, flux has no third harmonic. Flux is sinusoidal. That is in delta connection. And whenever I has no third harmonic, flux will have third harmonic. That is in star connection. But both these possibilities are only for the 5-limbed type of transformer. Okay. In case of 3-limbed transformer, doesn't matter whether the connection is star or delta, flux cannot have a third harmonic because flux does not have any closed path to flow. That means in case of 3-limbed type of transformer, flux will always be sinusoidal. But in case of 5-limbed type of transformer, flux will be sinusoidal based on whether the connection is delta or star. In case of delta connection, flux is sinusoidal. In case of star connection, flux is non-sinusoidal. And it has a third harmonic. Okay, this is about the construction of 3-phase transformer. Now let us see various type of 3-phase transformer based on connections. First is delta-delta connection. So there are few things to be kept in mind when we are using the 3-phase transformer. First is primary side will always have uppercase notation, that is A1 and A2 are in uppercase, and secondary side will have in lower case. So while drawing the phasor diagram for a 3-phase transformer, we will first draw the phasor diagram of a primary side, and based on that we will draw the phasor diagram of the secondary side. Okay. So we know we are assuming first of all positive sequence, that is if this is A, that is if this is A, this will be B and this will be C. Okay, that way we are assuming the positive sequence. So let us first draw for the primary side. Let me say I am assuming A1, A2 like this. That is my A phase. Now B phasor will lag this by 120 degree. So this is going like this. It will lag by 120 degree like this. Now A2 is connected to B1. So this will be B1, B2. Now this is going like this. C will lag by 120 degree like this. This will be my B2 is connected to C1, C1, this will be C2. Now if you see the output terminals are A2, B2 and C2. So in phasor diagram representation, I will remove this subscript 1 type of terminals, that is B1, C1 and A1. Okay. But first let us draw for secondary winding. I hope you understand. First I draw A phasor, then B will lag A by 120 degree and C will lag B by 120 degree. Always remember, the phasors for the delta connection will be drawn in the form of triangle. Now if we talk about secondary, we will draw like this for A1 and A2. Now A2 is connected to B1, we will draw like this, B1 and B2. I am drawing the phasor directly parallel to the primary, and this will be C1 and C2. This will be my secondary phasor which are parallel to the primary. Now here output is taken from A2, B2 and C2, output is taken from A2, B2 and C2. So let us remove the subscript 1. Okay, I am removing wherever the subscript 1 occurs. Okay, now to know the phase shift, what we have to do is we have to draw the reference phasor. How to draw reference phasor? Like this. Okay, draw a star in delta. Wherever we have touching A, this vector is touching A terminal, mark it as A. It is touching B, it will be B. It is touching C, it will be C. Similarly here it will be A, B, C. I am using lowercase letter for the secondary side. Now if we draw these two phasors on a clock, this A phasor is coming like this, vertical, and small a is also vertical like this. So it is as if the clock is showing 12 o'clock. So we will mark it as DD12. First letter should be capital, D denotes delta, capital denotes primary, and other D denotes delta and it denotes secondary. And on the clock it is 12 o'clock, so it is DD12. That is how we draw the phasors for a 3-phase transformer. Always keep it in mind that whenever this A phase is drawing, okay, this must always be vertical. No matter whatever connection you take, this will always be like this because it is used as a reference to determine the phase shift. Since here both are in phase, so here we have a 0 degree phase shift between primary and secondary. Both primary and secondary voltages will be in the same phase. Next, let us change this connection a bit. So first of all, let us draw primary phasors A1, A2, B1, B2 and C1, C2. A1, A2, B1, B2, C1, C2. Okay, because primary side is unaltered, it is same. Now let us draw the secondary phasor. I will draw like this, A1, A2. Now this A1 is connected to B2. So if A1 is connected to B2, the B phasor will be like this. This will be B2, B1. Okay. Now B1 is connected to C2. So it will be like this, C2, C1. Okay. That is how we have to draw the triangle. A1 and B2 must be same point. A2 and C1 must be the same point. And B1 and C2 must always be same. Now here output is taken from A1, B1 and C1. So let us remove the subscript 2. Okay. Like this I am removing the subscript 2. And here the output is taken from A2, B2 and C2 in primary. So I will remove the subscript 1. Now let us draw the reference phasor A, B, C. Here we will draw reference phasor. This will be A, B, C. Now if we draw on a clock, A is like this and small a is like this. That means it is as if the clock is showing 6 o'clock. So it will be DD6. And if we see A and A, small a are in opposite phase, that means we have a 180 degree phase shift. So delta delta transformer can provide two type of phase shift, that is 0 degree and the 180 degree phase shift. That is the property of a delta delta type of transformer. Okay. Now the thing is, the EMF equation that we derived for a single phase transformer, that is EMF is 4.44 Fn phi. But in case of 3 phase it becomes N phase and this becomes E phase. Okay. That is, N phase is number of turns per phase, E phase is the phase EMF. So if we take E phase primary by E phase secondary, it will be N phase primary by N phase secondary, or we can say simply NP by NS. Now I know in delta connection line voltage is same as phase voltage. So what I can write down is line voltage primary by line voltage secondary. Okay. That means phase to phase turns ratio or line to line ratio is same in case of delta connection, because line voltage and phase voltage is same. So phase to phase ratio and line to line ratio is same. Okay. Now what is the difference between star connection and delta connection is between the voltages. Suppose I say VL star is equal to line voltage in delta. So phase voltage in star would be line voltage by root 3, but phase voltage in delta will be equal to line voltage. Okay. That means phase voltage in delta is more as compared to phase voltage in star. Okay, that I can write down. V phase delta is greater than V phase star. That means N phase delta should be greater than N phase star. So delta delta connection requires more number of turns as compared to star star connection. Okay. Let us talk about currents. If we keep line current same, let us say IL star is equal to IL delta. Now I phase star we know will be same as line current in star, and I phase delta will be equal to IL by root 3, that is 0.577 IL. So phase current in delta is lesser as compared to star connection. So what does this happen is, I told you current rating is determined by the area of cross section of the conductor. I is directly proportional to area. That means area of conductor in delta is 0.577 times of area of conductor in star. So a delta delta connection requires more number of turns, but the winding is of a thin conductor. Okay, thin conductor and more number of turns are required in delta delta connection as compared to star star connection. Now we saw phase voltage in delta is more as compared to phase voltage in star. That means insulation requirement is more. Okay, insulation requirement is more as compared to the star connection. So this connection can be used for low voltage and high current rating. How I am saying it is, how we can find out the application. First let us keep insulation same. If insulation is same, that means phase voltage in star is equal to phase voltage in delta, because insulation determines the voltage rating. But VL star is equal to root 3 V phase and VL delta is equal to V phase. So it has a low voltage rating. As compared to star connection, it has a low voltage rating. Now if you keep area same, area of cross section of conductor is same, that means I phase star is equal to I phase delta, but IL star is equal to I phase but IL delta is equal to root 3 I phase. That is, it has high current. So if you keep insulation level and area of cross section same for both star and delta connection, that means that then the delta delta connection has a lower voltage rating and higher current rating. Okay, and here both the sides have closed path for the flow of third harmonic current. So here third harmonic current can exist, so flux can be sinusoidal. That is the features of the delta delta connection. So let us summarize what we have covered in this lecture. First of all, we started from power versus distribution transformer. There we saw in power transformer full load copper loss is critical, in distribution transformer iron loss is critical. Then we saw harmonics in three phase. We saw 3n plus 1 and 3n minus 1 harmonics are always present, but for triplen harmonics to be present we need a closed path or we need a path to the ground. So triplen harmonics can exist in star with grounded neutral or in a delta connection. Then we saw core and shell type transformer. We saw in core type transformer third harmonic flux can never exist because of absence of any closed path. In 5-limb type of transformer, third harmonic flux can exist in star connection but not in delta connection. Then we saw delta delta connection. We saw it is used for 0 degree phase shift or 180 degree phase shift, and we saw it is used for low voltage and high current application, and it provides a path for third harmonic currents, so flux can be sinusoidal. And we saw third harmonic current can exist in delta connection only in phase, but they are absent in the line currents. Third harmonics are only present in phase currents. In our next lecture, we will see a few more connections on the three-phase transformers like star star, star delta and delta star. That we will cover in our next lecture.